Okay, so we're going to start our adventure into trigonometric identities. So the very first section of chapter 7 covers basic trigonometric identities. We're going to look at reciprocal identities, quotient identities, and Pythagorean identities. Um, they're used to find trig functions given if given a trig function. Variations of the Pythagorean identities are as follows. Okay, so the very first Pythagorean identity, the most important one, is sine squared x plus cosine squared x is equal to 1. Now we have to remember our definitions of our trig functions. Now remember, by definition, the unit circle is x squared plus y squared. So I have to make sure that the mic was and that means that if y is sine theta and x is cosine theta, then also sine squared x plus cosine squared x is equal to 1. Now this is really saying y squared plus x squared is equal to 1, but addition is commutative, so that's not a problem. And you should be able to rearrange these identities into different forms. For instance, cosine squared x is equal to 1 minus sine squared x. Well, that also means that x squared is equal to 1 minus y squared, algebraically. We could also say that y squared is equal to 1 minus x squared. Okay, so we can rearrange these trigonometric equations just like we could rearrange an algebraic equation. So we want to keep that in mind. And this all comes from the definition of our basic trig functions at a unit circle. Okay, some other ones come up. Another one would be 1 plus cotangent squared theta is equal to cosecant squared theta. And that could be rewritten to be cotangent squared x is equal to cosecant squared x minus 1. Another one would be tan squared x plus 1 is equal to secant squared x. Now, I'm not going to get into the derivation of these formulas, just understand that they have been proven to be true. And just like this offset that says tan squared x is equal to secant squared x minus 1. So be able to rewrite these in all their different forms, and it will help you solve trigonometric problems, trigonometric equations, things like that. And this is very useful in calculus because oftentimes in calculus you will have to try to integrate something and you will need to rewrite your expression into something that's more simple. And these will help you do that. Now let's go through our reciprocal identities. 1 over sine theta is equal to cosecant theta. Well, that means that sine theta times cosecant theta is equal to 1. So again, you can rearrange these formulas. 1 over cosine theta is equal to secant theta. That also means that cosine theta times secant theta is equal to 1. Remember, reciprocals products are equal to 1. And 1 over tan theta is equal to cotangent theta. And also tan theta times cotangent theta is equal to 1. So be prepared when you're given an identity to rewrite it in all the different forms, all possible forms, and it will help you. Again, if you pause the screen, I'm going to scroll and discuss the identities. Quotient identities, well, tan theta is equal to sine theta over cosine theta. We know that already. Cotan theta is equal to cosine theta over sine theta. And again, we know that already. Okay, so how could we write those differently? Well, tangent theta times cosine theta must equal sine theta then. Or cotangent theta times sine theta must equal cosine theta. So be comfortable with rearranging these algebraic, moving your equations around. Now, tan theta divided by sine theta is equal to 1 over cosine theta. So when we do a different type of division, then that might give us secant theta. Cotangent theta divided by cosine theta is equal to 1 over sine theta, which is equal to cosecant theta. So a lot of little amazing identities come out of these once you start working with them. Okay, so you can pause the screen if you need to. That's it. What we have to see on this, and I'm going to go to the next screen. So sometimes when we're solving these, they give you a trig function and you have to find another trig function. Sometimes these identities are useful. Oftentimes I will end up drawing a triangle like we did in chapter 5 because that's just as useful and it's not as confusing. So we will use these identities a little bit later in the lesson, but for right now we'll use the simple ones. Otherwise we'll do it with like I said, the normal bow type of problem. This first one says if secant theta is equal to 3/2, find cosine theta if theta is between 0 and -0. The first thing you got to realize is where you are. Okay, so now we know that secant theta and cosine theta are reciprocals of each other. So we can simply solve this without making a triangle by simply flipping the fraction. So if secant theta is equal to 3/2 and quadrant 1 is where the angle is, then it must be 2/3, right? So the reciprocal identity tells us that. Okay. Now in this next problem, it says if cosecant theta is equal to a -4/3, find tangent theta if 180 is less than or equal to theta, which is less than 270. So that means I'm in Q3, right? Now, when I look back at my identities, I don't really see an easy way to go about this one, I don't think. When I go back and I look at my basic identities, when I go back and look, cosecants with cotangent and stuff like that. So I think I'm probably just going to do the whole try to prove bow tie method. So first off, I know if they give me cosecant that my reciprocal identity is sine, right? So that is using one identity. So I can say that sine theta is equal to a -3/4. Remember, sine is opposite over hypotenuse, or it's y over r. So we can draw a triangle and we can solve for the missing side, which is x, right? So we can say 4 squared minus a -3 squared is equal to the x part that we're missing. And so that's going to give us 16 minus 9 is going to equal 7, which is equal to x squared. So x must equal the square root of 7, and x must be negative because it's in the third quadrant. So we can say this is the negative square root of 7. Now I know all the sides, I can find tan theta quite easily because tangent is opposite over adjacent. So that's opposite, that's adjacent. I should be able to solve this quite easily. So sure enough, we get our Pythagorean theorem worked out, and we write our tan theta to be -3 over -7. And then 2 negatives will make it positive, but we need to rationalize it. And we get tan theta to be 3√7/7. Positive if you need to. I'm going to go to the next screen. So remember, when we do this, our job is to draw the part of the bow tie that represents the quadrant that they want, right? Remember, that's our goal. And this time we were down in Q3, so we were drawing that part of it. Okay. So if tan theta is equal to 2/5, find cosine theta. So again, probably it's better off just for me drawing a triangle again. It looks like we're in Q3. So why don't you give this a shot and see if you can find cosine theta, and come back, and once you're done, and all of the problem. Okay, hopefully you had time to work it. We need to make a triangle first in quadrant 3, so we're going to do that. Now, we know opposite, we know adjacent, which means we know y, and we know x. Both y and x have to be negative because we're in the third quadrant. So we do a -5 squared plus -2 squared to get r squared, and then r ends up being the square root of 29. Now remember, r is always positive, so we just don't even need to worry about that. So We know x, we know y, we know r, we can find cosine. Now cosine theta should equal x over r. So x in this problem is -5. And if r is square root of 29, you can rationalize it. So you should end up with -5 square root of 29 over 20. Pause if you need to. I'm going to the next screen. Okay, here's what I'll work two different ways. I'll work it using the triangle method, then I'll work it using the Pythagorean theorem to show you get the answer both ways. So they want me to find tan theta. They've given me cosine theta. Well, they say cosine theta is equal to, let's call that 21 over 100. So because I like working with fractions when it comes to that. It also tells me that I need quadrant 4. So cosine's positive, but tangent's going to be negative whenever I find it, because tangent's negative in the fourth quadrant. And if you recall, use your ASTC chart to determine that. Now, I mean quadrant 4, so I draw that part of the bow tie, and I'm saying that the hypotenuse is 100, and the x value is 21. So I am looking for, what is that? The y side, I'm looking for the y value, and we know that's going to be negative, so we have to take that into account. So 100 squared minus 21 squared should give me the y squared. So and I need the square root of that, so I don't think it's going to square root easily, so it's going to be some ugly number. That's my fault. Because I decided to change an ugly decimal to a fraction. So we need the negative, don't we? Because y is in the whole fourth quadrant. So now we get this to be a negative 955. Now they want to know tan theta. Tan theta is equal to that negative 9559 over what? 21. So that's going to be y over x, right? So now we can just get a decimal for this. They gave us decimals, we can give them decimals back. I can say alpha 1 equals negative square root 9559 over 20. It gives me a negative. So this is approximately a negative 4.656. As my answer for tan. Now, using a Pythagorean identity on the same problem, I would say sine squared theta plus cosine squared theta equals 1. And I know cosine is 0.2. So I gotta say 0.21 squared plus sine squared theta is equal to 1. I'm going to do 1 minus 0.21 squared, and that's going to give me the 0.9559, which I then have to square root. So we're saying that right now, we're saying sine squared theta is equal to 0.9559. Square root that. And it gives us 0.9777. Okay, so sine theta to a negative 0.977, let's say 7, because we're in Q4. You have to remember your location. The calculator's not going to give you the sign. You've got to remember the sign from the ASTC chart. So now we can do tangent theta by saying that number. I can just say alpha 1 equals enter, and I can recall that last value, right? Or I can, if I don't want to do that, then I can hit second negative, and that'll bring it up over 0.21. And I need to go back up to the top and put a negative in there, don't I? Because the original didn't happen. And it gives me the same answer. So using a Pythagorean identity will get me there. Using the bow tie method will get me there. Okay, so you have to decide which one is best for you. So you use that particular type because you have more than one way to solve that problem now. So I'll put that back up and pause the screen if you need to. I'm going to the next. Okay, so now we are going to start looking at trig identities. So don't forget your basic trig definitions. You already have these. These are in your section 5.3 notes. Okay, so just remember this information right here. Okay, sine is equal to y, cosine is equal to x, tangent is equal to y over x, and their reciprocals are equal to their reciprocals. And then also remember that it came from that basic triangle where your radius was 1. And just, I'll scroll this slowly. I'll go back up to the top and I'll scroll this so slowly so you can. You can pause it as you need to. This is prior learned information that's very useful with this stuff. Okay. Going to the next screen, so pause it if you need to. Okay, so basically we're going to simplify some trigonometric expressions. So in other words, we want to try to get this to be in the form of a single trig expression, not multiple trig expressions. Now they tell us that we know sine of A, and we know we have the product of sine A and cotangent of A. There's some different methods you can use, okay, but oftentimes you're going to do something algebraic to it. Okay, you can always change everything into terms of sines and cosines and simplify it that way. You can always look to factor something out if it's not a monomial. And you can always look if it's a fraction to get a common denominator. These are things you will do. I will show you the trig way and I'll show you the algebraic way, and I don't care which way you use. Okay, so the first thing we'll do is rewrite cotangent. So sine A over 1 times cosine A over sine A. That's the first thing. Now, at this point, I'm going to cross out my sine A's, and then my answer should just be cosine A. So I've rewritten this trigonometric expression into just one simple trig expression. So now, what would this look like algebraically? Well, algebraically, sine would be replaced with a y, and cotangent would be replaced with x over y. So you would be looking at that, and you would be trying to simplify this. So you would put the y over 1, and you would see that your y's cross out. And you're simply left with x, which is equal to cosine. So by definition, algebraically, if we simplify the algebraically equivalencies, we get the same answer. We just have to write it back in terms of the trig function. So simplifying usually yields one trig function. Okay, pause if you need to. I'm going to. Okay, we're going to try to simplify sine theta plus sine theta times cotangent squared theta. One thing we notice automatically is that this is not a monomial, so we're going to try to do a GCF. We're going to try to factor something out of here. It looks like they have a sine theta in common, so sine theta is going to go to the outside. So if I divide the sine theta to the outside, then it goes to the outside, and sine theta divided by sine theta leaves a 1, and then sine theta times cotangent squared theta over sine theta leaves cotangent squared theta. Now, as soon as we see some squares, we want to look at our Pythagorean identities. Okay, so now if you recall, 1 plus cotan squared theta is equal to cosecant squared theta. So we just do the Pythagorean identity. and replace it with its equivalency. So now we can rewrite cosecant as sine. So that's going to be sine theta over 1 times 1 over sine squared theta. So this is a reciprocal identity. And then we can cross out one of the sine thetas with the square on the bottom. And that's going to leave me 1 over sine theta, which is then equal to cosecant theta. So my final answer is cosecant theta. Now, the original problem said it was sine theta times sine theta plus, so it was sine theta y plus y, and then times x squared over y squared. That was the first. So if I see that expression algebraically, the first thing I'm going to do is try to factor out y. So if I factor out y, what's going to be left? 1 plus x squared over y squared. So then I'm going to get a common denominator. So that's going to be y squared plus x squared over y squared times y squared, times y, I'm sorry. Now, x squared plus y squared is equal to 1 because that's the unit circle. So we can say that y times 1 over y squared, and then we can say that's just equal to 1 over y, which is equal to cosecant theta. So I used an algebraic format to solve that, or I use a trigonometric form to solve it. Both are fine to use. Pause if you need to, I'm going to the next. Okay, you try to work this one, write it down, pause your screen, give it a shot, and then come back. Okay, and I'll try to work it both ways to see it. Okay, so go ahead and get to work, pause your screen. Okay, you're back. First thing we do is we factor out a sine squared. We see 1 plus tan squared theta. That's a Pythagorean identity. That's Pythagorean, so that's going to be equal to secant squared. I can rewrite secant squared as reciprocal identity using 1 over cosine. So we have sine squared over 1 times 1 over cosine squared theta. That's going to be sine squared theta over cosine squared theta, which should give me tan squared theta. Now, what would this look like algebraic? Well, that's going to be y squared plus y squared times y squared over x squared. And then we can factor out the y squared. That's going to give me 1 plus y squared over x squared. Common denominator. And that's going to be y squared times x squared plus y squared over x squared. You know this is equal to 1. So it's going to be y squared times 1 over x squared, which is equal to y squared over x squared, which is equal to tan squared theta. Now it's in the form of a single trig function. It doesn't have to be to the first power. Okay, so just keep that in mind. Pause if you need to. I'm going to the next part. Okay, so you give this one a shot, see how you do, and come back on off pause and see how if you got it right or not. Okay, you're back. So the first thing I'm probably going to do is write everything in terms of sines and cosines. So I'm going to say 1 over sine x is cosecant x, and then cosine x times cotangent x is cosine x over sine x. So one thing I notice right away is that my denominators match. Okay, and I also notice I got a cosine squared in the numerator, which is a good thing. So 1 minus cosine squared x over sine x. So 1 minus cosine squared x should probably be sine squared x. Oh, right, it's a single term denominator. So 1 minus cosine squared x should be sine squared x. So sine squared x divided by sine x should just be simply sine x. Now, the original problem, hold on just a second, I'll write this down. That's 1 over I minus x times x. Let's see the answer. So we say, first thing we want to do is notice that the bottoms both have a y. So we can write this as y minus x squared over y. Y minus x squared is equal to y squared over y. Y squared over y equal to y, which is just equal to sine x. So depending on how you see it, some people like the algebraic pattern, some people like trigonometric function. Either way, you get it simplified. Now, in trig or in calculus, it's going to be a lot easier to integrate an expression that says just sine x versus an expression that says cosecant x minus the product of cosine x times tangent x. So keep that in mind as you're looking at this stuff. Okay. You can pause if you need to. Okay, last one of these, so you can give it a shot. So you did, and pause it, come back online once you pick it up. Okay, we're back. We have cosine squared alpha times tan squared alpha plus cosine squared alpha. So I'm probably going to factor out a cosine squared alpha right away because it's not a monomial and there are common factors. So cosine squared alpha times tan squared alpha plus 1. Well, that's a Pythagorean identity right there. So I go look at my Pythagorean identities, and I see that that's equal to secant squared alpha. Well, cosine alpha and secant squared alpha are reciprocals of each other, so that should equal 1. We can rewrite it if we need to, but reciprocal means that their products make 1, and you're done. Now, I say this is x squared times y squared over x squared plus x squared, I factor out x squared. That's going to leave me y squared over x squared plus 1. And then I get a common denominator, x squared times y squared plus x squared over x squared. Top's equal to 1, so this leaves me x squared over x squared, which is just equal to 1. And you're done. Now that was the last part of the notes, so I'm going to stop